We start with Galileo's principle of relativity, which applies to frames of reference moving with uniform translational motion relative to one another. Already in Newton's first law, we emphasize that the fundamental laws of mechanics are valid not in arbitrary frames of reference, but only in inertial frames. In most of the problems studied so far we have chosen the Earth as the reference frame, while in the case of planetary motion we have used a frame associated with the distant stars, assuming that both can be regarded as inertial to a good approximation. To examine the validity of this assumption more carefully, and because it is often more natural to describe motion relative to moving objects such as vehicles, we shall now investigate how the laws of mechanics are affected when they are formulated in frames of reference that move relative to one another. We begin by considering frames of reference or coordinate systems attached to them, that move with uniform rectilinear motion relative to one another. A passenger traveling in a train that moves at constant speed along a straight track experiences no sensation of the train's motion, and the passenger sitting in a windowless compartment cannot determine by any mechanical experiment whether the train is at rest or in motion. The motion of a falling ball or a swinging pendulum appears exactly the same whether the train is stationary or moving uniformly, making it impossible to infer the train's speed from mechanical observations alone. As a result, the laws of mechanics have the same form in a frame of reference attached to the train as they do in a frame fixed to the Earth. This observation leads to Galileo's principle of relativity, which states that all reference frames moving with uniform translational motion relative to one another are equivalent for the description of mechanical phenomena. More generally, the principle of relativity is a principle of Galilean invariance asserting that the laws of physics have the same form in all inertial frames of reference, that is, for all observers moving at constant velocity relative to one another. Consequently, if one of these frames is inertial, every other frame moving uniformly relative to it is also an inertial frame. Galileo had already recognized the equivalence of rest and uniform rectilinear motion through his famous ship experiment, but the principle was later formulated more generally in terms of inertial reference frames within Newtonian mechanics. To illustrate the principle of relativity, consider two coordinate systems K and K' attached to frames of reference moving uniformly relative to each other. That is, K' moves with a constant translational velocity v0 relative to K without rotational motion. Let the origins of the two systems coincide at the initial time t equals 0. Because the frames do not rotate relative to one another, the orientation of K' may be chosen arbitrarily at t equals 0 and remains unchanged thereafter. At a later time t, the vector pointing from the origin O of system K to the origin O' of system K' defined by the position vector R0, is equal to the product of the translational velocity v0 and the time t. Now we examine how we can describe motion in the two frame of references endowed with the coordinate systems K and K'. If the position vector of a point mass m is denoted by r in the frame K and r' in the frame K', then, as shown in the figure, the vector r is equal to the sum of the vectors r' and r0. Or the position vector r' plus the product of the translational velocity v0 and the time t, where the vector v0 is constant. Differentiating these equations with respect to time gives the relation between the velocities measured in the two frames. That is, the derivative of the position vector r with respect to the time t is equal to the sum of the derivative of the position vector r' with respect to the time t and the velocity v0. Or the velocity v of the point of mass in K is equal to the vector sum of its velocity v' in K' and the constant translational velocity v0. Differentiating once more yields the corresponding relation for the accelerations. Since the translational velocity v0 is constant, its time derivative vanishes, and therefore the second-order derivative of the position vector r of the point mass is with respect to the time t is equal to the second-order derivative of the position vector r', or the acceleration a of the point mass in K is equal to its acceleration a' in K'. The acceleration of the point mass is therefore identical in both coordinate systems. The force F acting on the point mass is the same for observers in both K and K', since it depends only on the position and velocity of the point mass relative to the other bodies, as well as on time. As these quantities are identical for both observers, they assign the same force to the point mass. Because both the acceleration and the force are invariant under a uniform translational transformation, the fundamental equation of dynamics and the principle of action and reaction retain exactly the same form in both coordinate systems. Consequently, Newton's second law takes the same form in both frames of reference. In the frame K, the mass m of the point mass multiplied by the second-order time derivative of its position vector r is equal to the force F, while in the frame K', the mass m multiplied by the second-order time derivative of the position vector r' is equal to the same force F. The physical force is the same geometric vector in both frames of reference. Its magnitude and physical direction are invariant, while only its components with respect to the coordinate axes may differ. If the coordinate systems k and k' have the same orientation, the force has identical components in both systems. Otherwise, its components in k' are related to those in k by a rotation matrix. As an example, let us consider the free fall of a body, where an observer at rest in the frame k releases a body of mass m from rest at the time t equals 0. The motion of the body is described by Newton's second law, stating that the product of the mass m times the second-order time derivative of the position vector r of the body is equal to the product of the mass m and the gravitational acceleration g. Solving this equation with the initial conditions r at 0 equals 0 and v at 0 equals 0 yields the familiar equation of free fall, stating that the position vector r of the body is given by the gravitational acceleration g times the square of the time t over 2. Likewise, an observer at rest in the frame k' starts from Newton's second law formulated in k' and obtains the same equation of free fall. With the initial conditions r' at 0 equals 0 and v' at 0 equals 0, the solution is the gravitational acceleration g times the square of the time t over 2, which is identical in form to the solution obtained in the frame k. The two coordinate systems are therefore completely equivalent for the description of all mechanical phenomena, since every mechanical process can ultimately be reduced to Newton's second law and the principle of action and reaction. Newton's concept of absolute space has no physical meaning because according to the principle of relativity, an absolutely stationary frame of reference cannot be distinguished from a frame moving with uniform rectilinear motion relative to it. As we shall see later, this indistinguishability holds for not only of the laws of mechanics but for all physical phenomena. We have already seen that the relative orientation of the coordinate systems k and k' plays no role in the principle of relativity. We may therefore consider the most general transformation between two coordinate systems attached to two reference frames moving with uniform translational motion relative to one another. Such a transformation includes not only a constant rotation of the coordinate axes and a constant translation of their origins, but also a transformation of the time coordinate. We now introduce the Galilean transformation G, which maps one inertial reference frame into another described by one vector equation and one scalar equation. The vector equation transforms the position vector r in the frame k into the position vector r' in the frame k' that is equal to the product of a constant rotation matrix R and the position vector r, plus the translational velocity v0 times the time t, plus a constant spatial translation vector r0. Here we use the plus sign for the so-called boost term v0 times t because it defines a physical passive transformation mapping from the coordinate system k to k', or it defines the motion of the moving frame's origin moving away from the stationary origin in the positive direction. When studying the spatial rotations of rigid bodies about a fixed point, we showed that the rotation matrix R is an element of the orthogonal group of 3 times 3 matrices and therefore its determinant equals plus or minus 1. If its determinant is equal to plus 1, the transformation represents a proper rotation of the coordinate axes. If the determinant is equal to -1, it represents an improper rotation, that is the composition of a proper rotation and a spatial reflection. In the scalar equation of the Galilean transformation, the time coordinate t in the frame k is mapped into the time coordinate t' in the frame k' that is equal to epsilon times the time t, plus a constant time shift t0, where epsilon can be equal to plus or minus 1. Epsilon equals -1 corresponds to time reversal. Let us now determine the number of independent parameters of the Galilean transformation. The rotation matrix R specifies the relative orientation of the coordinate axes in the reference frames k and k'. Since every proper rotation in three-dimensional space is determined by 3 independent parameters, for example the Euler angles, it contributes 3 continuous parameters. The velocity vector v0 specifies the constant translational velocity of one frame relative to the other, and contributes 3 additional continuous parameters through its Cartesian components. The translation vector r0, which determines the relative position of the origins of the two coordinate systems, contributes further 3 continuous parameters. The time translation t0 representing the difference between the origins of time in the two frames, contributes 1 continuous parameter. Finally, the parameter epsilon describing the possible time reversal, is a discrete parameter. Consequently, the Galilean transformation is characterized by 10 continuous parameters and 1 discrete parameter. Let us now determine the composition of 2 Galilean transformations. Suppose that the first transformation G' maps the coordinates of an event from the reference frame K to the reference frame K'. That is, it maps the position vector r to the position vector r' by multiplying r by the rotation matrix R', adding the product of the velocity vector v0' and the time t, and finally adding the translation vector are not prime. At the same time, the time coordinate t is transformed into t prime by multiplying t by the parameter epsilon prime and adding the constant time shift t naught prime. Now suppose that a second Galilean transformation G double prime maps the coordinates from the reference frame K prime to a third reference frame K double prime, acting on the position vector r prime and the time coordinate t prime. It transforms r prime into the position vector r double prime by multiplying it by the rotation matrix capital R double prime, adding the product of the velocity vector v naught double prime and the time t prime, and then adding the translation vector r naught double prime. Similarly, the time coordinate t prime is transformed into t double prime by multiplying it by the parameter epsilon double prime and adding the constant time shift t naught double prime. Let us substitute the two equations describing the first Galilean transformation into the vector r prime and the time coordinate t prime in the vector equation of the second Galilean transformation. By removing the parentheses and factoring out the time coordinate t, we can write the right-hand side of the equation as the product of the matrices capital R double prime and capital R prime multiplied by the vector r, plus the sum of capital R double prime times v naught prime and v naught double prime times epsilon prime, times the time coordinate t, plus the vector sum of three constant vectors, v naught double prime times t naught prime, capital R double prime times r naught prime, and r naught double prime. Since the product of two orthogonal matrices is always an orthogonal matrix, that is the product of two matrices of rotation is another matrix of rotation, the matrix capital R defined by capital R double prime times capital R prime is also a matrix representing spatial rotations. We can also define the vector v naught by the sum of capital R double prime times v naught prime and epsilon prime times v naught double prime, and the vector r naught by v naught double prime times t naught prime, plus capital R double prime times r naught prime, plus r naught double prime. If we apply these definitions in the right-hand side of the equation, we can write the position vector r double prime as the product of the matrix capital R and the vector r, plus the vector v naught times the time coordinate t, plus the vector r naught. Similarly, by substituting the scalar equation of the first Galilean transformation into the scalar equation of the second Galilean transformation, we can write t double prime as the product of epsilon double prime and epsilon prime times t, plus epsilon double prime times t naught prime, plus t naught double prime. If we introduce the parameter epsilon for the product of epsilon double prime and epsilon prime, and the parameter t naught for the sum of epsilon double prime times t naught prime and t naught double prime, then the time coordinate t double prime can be written as epsilon times the time coordinate t plus t naught. By inspecting the expressions obtained for the position vector r double prime and the time coordinate t double prime, we observe that they have exactly the same form as the vector and scalar equations defining the Galilean transformation. The rotation matrix capital R describes the transformation of the coordinate axes from the reference frame K to the reference frame K double prime. The velocity vector v naught represents the constant translational velocity of the reference frame K relative to the reference frame K double prime, while the translation vector r naught specifies the position of the origin of K double prime with respect to the origin of K. Likewise, the parameter epsilon determines whether the direction of the time t double prime is preserved or reversed, whereas the constant t naught specifies the shift between the origins of time and the reference frames K and K double prime. We therefore arrive at the following important result: the composition of two Galilean transformations is again a Galilean transformation. Another important property of the transformations mapping inertial reference frames into inertial reference frames is their affine character. The Galilean transformation G is an affine transformation, that is, it maps straight lines to straight lines and the ratios of distances between points on a line. In other words, G preserves collinearity, that is, if a collection of points sits on a line before the transformation then they all sit on a line afterwards, and also preserves the ratios of distances along a line, but it does not necessarily preserve lengths or angles. Such a transformation moves or changes a shape using translation, rotation, and scaling while keeping straight and parallel lines intact. Affine transformations mapping a vector x to a vector x prime are generally represented by the vector equation stating that the vector x prime is equal to the product of a matrix A and the vector x, plus a translation vector b. Here, the matrix A represents the linear part of the transformation, while the vector b specifies the translation. The Galilean transformation can therefore be regarded as an affine transformation acting on four-dimensional spacetime vectors. It maps the four-dimensional vector formed from the position vector r and the time coordinate t in the reference frame K into the corresponding four-dimensional vector formed from the position vector r prime and the time coordinate t prime in the reference frame K prime. The transformation is represented by the product of a 4x4 matrix and the four-dimensional spacetime vector, followed by the addition of a four-dimensional translation vector formed from the spatial translation vector R0 and the time translation T0. The transformation matrix itself is composed of the rotation matrix R, the velocity vector V0, a three-dimensional zero-row vector, and the parameter epsilon. The homogeneous coordinate representation allows affine transformations to be written as pure matrix multiplications by introducing one additional coordinate equal to 1. In this representation, the Galilean transformation maps a five-dimensional homogeneous vector, obtained by appending the coordinate 1 to the four-dimensional spacetime vector formed by the position vector r and the time coordinate t, into another homogeneous five-dimensional vector by means of a single 5 times 5 matrix multiplication. This matrix is constructed by augmenting the 4 times 4 matrix of the Galilean transformation with the spatial translation vector R0 and the time translation T0, as shown in the vector equation. Consequently, both the linear transformation and the translation are incorporated into a single matrix, allowing the Galilean transformation to be represented as a purely linear transformation in homogeneous coordinates. The homogeneous coordinate representation also implies that the composition of two Galilean transformations is represented simply by the multiplication of their corresponding 5 times 5 matrices. Likewise, the inverse of a Galilean transformation is obtained by inverting the matrix representing it. As a result, the Galilean group is realized as a matrix group acting on homogeneous spacetime coordinates, that is, the homogeneous coordinate representation provides a faithful matrix representation of the Galilean group. In other words, the set of all Galilean transformations forms a group under the operation of composition, known as the Galilean group. This group is denoted by Gal3, where 3 refers to the number of the spatial dimensions in Newtonian mechanics. Restricting the transformations to proper spatial rotations and excluding time reversal yields the proper orthochronous Galilean group Gal plus 3. This group satisfies the following axioms. The composition of any two Galilean transformations G double prime and G prime is again a Galilean transformation, establishing the closure relation with a well-defined binary operation on the group. Here the rotations, the boost, and the space and time translations of the result G of the group operation have already been computed in the previous point. The composition operation is associative, a property that follows directly from the associativity of matrix multiplication in the homogeneous coordinate representation. The group contains an identity element E corresponding to the transformation with no rotation, no boost, no spatial translation, and no time translation. That is, for the identity element E the rotation matrix is a unit matrix, the vectors of the boost and the spatial translation are null vectors, and the time shift is 0. Every Galilean transformation possesses an inverse, obtained by reversing the rotation, the boost, and the spatial and time translations, so that applying the inverse transformation restores the original coordinates of every event. Here we also give the explicit forms of the rotation matrix, the vectors of the boost and spatial transformation, and the time shift for the inverse. With these axioms, the proper orthochronous Galilean group is a 10-parameter continuous transformation group, or equivalently, a 10-dimensional Lie group. It is generated by 3 spatial rotations, 3 Galilean boosts, 3 spatial translations, and 1 time translation.